Alright, so I thought I'd do one more where I did the whole shebang, where we actually sketch the curve at the end, we apply derivative tests, we do everything we need to do to be able to sketch f and all of its relevant information. Okay? And then I think I did change this assignment to be due on Monday, by the way. I don't think we're going to start anything tomorrow, so that should give you plenty of time. It's a big assignment. It should relieve a little bit of stress. I think we have time to make that work. As long as we get this unit done by spring break, we're in very, very good shape. So, all right, let's try again. So, you guys, remind me, what should we start out by finding? The first derivative, because the first derivative is going to tell us about critical points like maxes, mins, and saddles. Great. And then we're going to go on and find the second derivative because we need it for concavity and inflection points. Great. Okay. So first derivative. Can you guys help me out with that? I guess it's your choice. What should we do? Quotient rule? Okay. We could use a product rule. I like the quotient rule well enough though. So how's that going to go? O D high, that's kind of nice, right? Minus, what's D ho? Oh, that's dangerous there, D ho. Okay. All over bottom squared. Okay, should we simplify it?
Yes.
Thinking, yeah, that goes away, right? So we have negative 12x over x squared plus 3 quantity squared. Okay, so shall we find our critical points? How are we going to find them?
Set it equal to 0.
Set it equals 0, or don't forget, you're going to have problems where you got to look at does not exist as well, because it could happen at a cusp or something like that, or an asymptote even. Could it happen at an asymptote where you get a max or min? No, I guess I lied there. But. So it's 0 where we only have to worry about the top, which is of course at 0 if you divide by negative 12, right? And the bottom we want to check as 0 to see if it doesn't exist anywhere. You can solve this equation, of course, which I'm going to. You can also think about it abstractly. I encourage you to do both. Abstractly, is this going to be 0 anywhere?
No.
No, why? You're squaring something that's strictly positive. What's the smallest this thing inside could possibly be?
3.
3. It'd be 3 if x was 0. So some people watching the video, and some of you might be wondering, well, couldn't you make it smaller than 3 if you put a negative number in for x? The answer is no. No matter what negative number you put in there, squared makes it positive, and it contributes even more to the 3, and then the squared outside makes it even bigger. So is this thing ever going to be 0?
No.
Conceptually, no. Let's see if it checks out algebraically. So to solve this, how would I solve? Square root right away. Square root always comes with plus or minus. Doesn't matter this time though, right? So that's just 0. X squared plus 3. Subtract the 3. Square root, and you get what?
Square root of a negative number.
Square root of a negative number, which is plus or minus root 3i here. It doesn't exist in the real number system. So since we're doing real valued calculus, we don't have to worry about it. If we were going to do complex valued calculus, we'd have to worry about it, but that's beyond the scope of what most people will do, even as an engineer, unless they do real high level stuff. So, okay? So there we go. So we just got one critical point. You guys want to use the first derivative test or the second derivative test to see what it is? First derivative test. Okay, so you're saying that, I'm guessing, because you don't want to take another derivative, right? So that's smart. But are we going to need to do another derivative in this problem anyway? We do, yeah, unfortunately, because we have to look for concavity. So I'm going to use the second derivative test since we've got to find it anyway. So we'll put that on pause and go and find our second derivative. See, that's how you should think about these problems. Be efficient. Do the least amount of work you have to. So f double prime. I should be shooting from this guy, right? So I'm going to do another quotient rule. Can you guys help me? No one wants to be on film? It's going to be... Okay?
Stop.
2 times the quantity, I like that. All over
2 times at,
Just that one.
yeah, just
that whole thing to the 4th power, right? Because it's whole squared. Okay, let's see if this simplifies, because that's pretty ugly looking, right? I think we're going to want to take some time to simplify this. You might even need to expand that out. Let's see. So I've got minus minus is plus, 2 times 2 is 4, there's an x there, and oh, there's a 12 there too, right? 4 times 12, 48x, that covers this, this, and those. Except I missed one of those things. What is it?
Oh, it's squared.
X squared, right? There's 2 x's. You guys see them? And then I've got an x squared plus 3 in there as well. Over x squared plus 3 to the 4th power. So now someone tell me, how can I simplify this? You could, of course, expand those out and get all the little pieces, but there's a smarter way on this problem.
You just divide it.
Okay, so someone tell me. I saw Gabe hand first. What'd you have, Gabe? Yeah, the x squared plus 3 is shared, right? This is just like an algebra 1 problem we were doing earlier. So how many of them does it share?
1.
Just 1. Is there anything else in common between these two? So you probably want to pull out everything.
Oh.
Should we just go for a 12? You guys want to do negative 12, positive 12? I'm going to pull out a negative 12. I don't know. I'm just going to see how it goes. It's kind of our choice on that one. So there's only one of these in common, so what's left? Let's see. Well, we pulled out everything here, right?
No, it's like
Wrong. There's still an x squared plus 3 to the 1 power, so I don't really need to write to the 1 power, do I? Then over here, I took that out. I took out negative 12 of the 48, so what's left?
4.
Negative 4, and I've still got my x squared there as well. X squared plus 3 to the 4th power on the bottom. Now what's going to happen? Yeah, this goes away totally, and I reduce this exponent to 3, nice. So let's see what's left now. So I've still got my negative 12, combine like terms in there, and you have negative 3x squared plus 3, right? Over x squared plus 3 to the 3rd power. We could, of course, distribute back our negative 12, but now I think I can look at the bottom and top and quickly make a decision about where there's 0. Does that make sense? So that's what you guys want to pursue. This kind of factoring on this problem is very essential. So make sure that you do that on yours. Right? It does take a little time, but it's important. Important mechanical stuff. So let's get down what we have so far. So I'm going to erase some of the stuff that we don't need. So let's leave our derivative up here in its simplified form, shall we? Leave that. Let's get our second derivative right next to it in its simplified form. So we'll say f double prime of x. And that guy was, should we distribute? I'm going to distribute that back. So I'm going to get what, 36 x squared. Distribute the negative 12 and you get negative 36. I don't know. I guess I could just factor that back out now. Tough call. And then we found that there was only one critical number, right? So let's write that down too. So we've got a critical point from this guy of x equals 0. Okay, so we had one critical point. I heard out there someone said 2 inflection points. Where are they pulling 2 inflection points from? Negative 1 and 1? Where's Derek looking at to obtain that? He's looking at the top. Do we just have to look at the top? Inflection points, just like critical points, you got to check where it's 0, which is the top, and where it doesn't exist, where the bottom is 0. The bottom's not 0 anywhere, though, is it? The same argument we used before applies, because this inside's never going to be less than 3, and whatever power you do to it, it's not going to ever make it 0, is it? So we don't have to worry about the bottom on this one. But the top, we've got a couple inflection points. Do it how you want. I think Derek was doing it by inspection or something like that. You could factor this guy and say 36 x squared minus 1. You Just your difference of squares. You can set it to 0, whatever. I think that's the nicest way to do it. That's a personal preference. So we've got 2 inflection points. So it should change concavity twice then. Okay? So I think we've got all the information we need. Let's put this in charts. We should be able to come up with our curve from those charts. All right? So first chart, I should compare f to f prime. So I guess I've decided to do the first derivative test, yeah? And for my concavity, I'll look at f versus the second derivative. So we need to cut this chart where? At 0. And this one we need to cut
1.
at -1 and 1. Okay. So how do I use these charts again? I need to select some what?
Points. Like
Test values, points, yes. So what would be a good one for over here?
1.
1. See how 1 is also an inflection point though? That should still work. I mean, it shouldn't be a problem, but you might just pick something else. Just so you don't get them mixed up or something, you know? So maybe like -1 and 2. So if I put 2, where should I be putting these test values in? Use the key on the chart. That's why you write it down in the first place. So I should be putting 2 into f prime. You could put it in any form of it. We had it simplified right here. The top is going to be -24. I just care that it's negative, right? And the bottom, we already agreed. What's the bottom always going to be regardless? It's going to be positive. So this guy is negative. If I put negative in the top, we get positive. Bottom's always positive. So that's positive. What's that tell us about the behavior of f?
That
Means it's increasing first,
Then decrease.
and then at 0 it starts decreasing. So now this should help you with curve sketching stuff that we've been kind of alluding to on several tests and quizzes and stuff in the past. This is really nailing it down and giving you a method to do it. Okay, so now I want to use these guys. Well, I should pick some test values first, so let's pick, this goes -2,
0.
let's go with 0. It doesn't really matter if you pick the same things. I mean, just got to do one chart at a time. And where am I plugging these in? Double prime. I'm going to do 0 first, that sounds easy. Gone, negative over positive is negative. And if I put 2 into the top, I might need to work it out, but
Positive.
I don't think we need to work that out, do we? Positive over positive is going to be positive. If I put -2 in the top, maybe we need to work it out. Squared's going to be positive. That's a big positive number minus something smaller. So that's going to be positive on top, and of course,
Positive.
positive on the bottom still? Even
Yeah.
though there's a 3 power here? Yeah. Okay, so what does that tell us? What's that information in that chart tell us?
It changes.
So what should I draw here?
like
A concave up shape, right? It doesn't have to be a parabola, but some kind of up shape. Some kind of down concavity shape, some kind of up concavity shape. So 0, what was it? We've got all the information. It was a maximum, right? You can see the maximum right there. And then we know what the concavity shape is going to be. So we can now obtain a nice sketch of the curve, or a poor sketch of the curve, depending on how good you are at drawing. So at 0 we have a maximum. If you want to know how high that maximum is, you could of course plug it into the original function. If I plug it into the original, how high does it go? F of 0 is 2, right? So it's going to be right here. There's the actual point, and it's a maximum. So it's going to increase up to that spot. But where was there an inflection point? -1. So it's supposed to start out concave up, and then at -1 it flips over. So at -1, I don't know, maybe it's like somewhere like this. There, it's concave down, that matches this. What should I draw from here? Should I draw a cusp? Then it wouldn't be doing this, right?
Could you go down like a curve like to an asymptote?
I don't think there's necessarily an asymptote, it just flips over. That's an inflection point. That's that inflection point that we're looking for. So I think over here it's probably like some kind of mirror image, right? So over here at 1, it's supposed to be concave down still until somewhere like that. That qualifies for this. Then it's supposed to flip concave up at 1, but it's supposed to stay decreasing that entire time. So something like this. Now, if you want to nail that down more accurately, you're going to have to plug in some more points, but that's not the point of this. We know all the relevant stuff. We know the maxes and mins, we've got them all. There's only one. We got all the inflection points. That's all you need to know about a function. I guess besides its zeros. So, questions? There's something horrendously wrong with this picture, by the way, if you think about the original curve and your knowledge of algebra.
It shouldn't be negative.
Something horrendously wrong with it.
It should never be negative.
They're saying it should never be negative. Why?
Because the bottom's negative and the top's the
Top's
bottom-
positive, always, it's always 6. The bottom's always
positive. Positive.
strictly positive. That tells you it should never be negative. So how can I make this still happen and fix that?
Just
Make it like a
squeeze
sine
it.
curve.
I like this sine curve suggestion. Can we maybe do like this? I think it's something like that. If you want to confirm that it actually has an asymptote at y equals 0, you could take a limit. Let's do it. The limit as x approaches infinity should be what from my picture? 0 or something like that, right? Is it? If you put a really big number in for x, you do the plug-in approach, you get what? 6 over
Big.
really big squared is even bigger, plus 3. That's going to be approximately,
It's not
if you go to infinity, it's 0, so that's making sense. Okay?
big until you put that 3.
All right.
Oh, yeah. No, 3 big.